Hi everyone, this is Steve Christensen. Welcome back. Today we're going to be talking about Chapter 2, Water Sources and Treatment. So everything starts with the hydrological cycle, and this is the kind of thing that actually shows up on the Grade 1 tests, Grade 2 tests on both distribution and treatment. So we know we have evaporation and transpiration, condensation, precipitation, infiltration, percolation, and runoff. So what happens? Well, we know we certainly have the evaporation that goes up into the clouds. It comes across, it comes down in the form of, rain clouds, snow. We certainly know that snow works as a reservoir up in the high country, so it's so critical for us here in the Sierras. It comes down and it goes down then, and it either percolates into the ground or it goes down through surface of creeks and rivers and all that kind of thing. And then it transpires up through the plants, transpiration from the plants. We also get evaporation, certainly, as we mentioned to begin with. But it's a cycle. It's a finite amount of water on this earth. Once the water falls from the sky, what happens? Well, one of the things to understand is water is a universal solvent, and it picks up things. Microorganisms, bacteria, viruses, protozoas, mineral substances, organic substances, and other forms of contamination. And there's about a zillion and one out there. So groundwater versus surface water. What are we talking about? Okay, groundwater, wells. Okay, normally in the cycle of wells, it comes up, and some well water actually is still so pure that it doesn't even need to be treated. I've worked on a system that had very pure water. But then normally, the rule of thumb is you disinfect. You go into a storage of some kind and out through the distribution system to your neighborhood. It gets a little bit more complex when we're talking about surface water. Surface water is going to have a lot more turbidity, and turbidity are the things floating in the water, the things that make water look murky. And there's a lot of viruses and protozoas, and there's clays and silts and everything else, every other kind of pollution in there that you could think about because it's exposed to the elements. When groundwater comes out of the well, it's actually been through nature's filtration system, which is the earth, all that sand and gravel and everything else. But the way it normally works is we go through and we get it out of a creek or a river, whatever. We do some preliminary treatment on it, and it goes through, and we do our coagulation and flocculation. Again, this is where we're adding some chemicals in. We're mixing it, and then it's allowing to basically group together and float down to the bottom. In a clarification basin, then, again, the balance of it floats out to the bottom, and the clean water is siphoned up on the top. And it goes down, and then oftentimes it goes through a softening and stabilization process into filtration, and it comes on out, and we might add a few minerals or things along the way to treat it. Fluoridation is common, and again, that's kind of a hot button, very controversial, but we always disinfect. And it basically goes out into the tanks and out into the distribution system. And when we disinfect, chlorine is normally the disinfectant of choice. And we always want to make sure that we get past to the point that we've done all the kill, but there's some extra, and that extra is called a residual. So what determines the treatment method? These four headings determine treatment based on regulations and customer satisfaction. We have the physical. The physical is the color, the turbidity, temperature, taste, odor. We have chemical, which is the fluorides, sulfides, acids, minerals. The biological, which is viruses, bacteria, algae, protozoas. The radiological, water may have to come in contact with radioactive substances. Up into the Sierras, there's a lot of uranium and heavy metals in the hills. Chemical analysis is broken down into three categories. General mineral, which is like alkalinity, calcium, copper, iron, manganese, pH, sodium, zinc. Inorganic chemicals, which are like toxic metals like arsenic, and nonmetals like fluoride and nitrates. And organic chemicals, which are volatile chemicals such as benzene, PCB, simonize, so on and so forth. The physical characteristics of water. These are 5 points you want to know. These will be showing up on the exams. Not only my exams, but the state exams. Color, odor, taste, temperature, and turbidity. And again, you look at these jars, and actually in the lab we do what's called a jar test. But anyway, to make a long story short, we've got low turbidity over here, pretty clear, and then high turbidity over here. So what are some of the other characteristics of water? Concerns for our customers. They want nice clear water. Look at that toilet bowl on the right. Obviously there's a lot of iron and manganese in that water. You can see by the staining. You want no scale deposits. Scale comes from hard water. You want it free of taste and odor. Now, taste and odor are one of those things that a lot of it actually are within guidelines, but you know what? Nobody wants their water to smell or taste bad. We want it corrosion free. The corrosion side of water can be really, really substantial. And this is, again, where that pH balance comes in. And again, we're looking ideally for 6.8 is the magic number between 0 and 14. And we certainly want it to be non-staining and non-scale producing. Water rights. This is something, again, this is an important page, so pay attention to this. Riparian. Riparians are rights acquired with land titled bordering a surface water source. You have a riverfront lot. Appropriative. Rights acquired for the beneficial use of water by following certain legal procedures. Prescriptive. The rights acquired by diverting water that others may or may not have prior claim to and using it for a specific period of time. A prescriptive is a limited deal. The appropriate side is, for example, public domain moves in and they say, hey, we've got a really good water source and we need to drill a well right here. And so that would be an appropriative right. So who owns that water? If there's a question regarding the right to use the water, you need to consult with appropriate authorities. Water rights is a huge deal, and it's just going to get bigger and bigger. You want to establish the right to use the water, secure the documentation in a safe location. There's a lot of water districts that think that they have water rights because they've never really documented them over the years, and all of a sudden they go to do some kind of big loan or something and they want to see the documentation of the water rights. It's a big drill because oftentimes they can't find them. So they have to go back through the state with attorneys and all kinds of stuff and reestablish those water rights. And you also want to be able to amend them legally when or if necessary. So surface water source quality. Well, we have the oceans, and we certainly are talking a lot about desalination these days. We're starting to see desalination come in more and more because the cost efficiencies are starting to make sense. There's a huge plant that's 1 billion gallon a day that's being done in Carlsbad. I'm sorry, not a billion gallon a day. I think it's 10 million, I believe is what it is. I'll have to double check on that. But anyway, we also then have direct runoff, which is rivers and streams, lakes and reservoirs. So quality. We certainly are really concerned about what's upstream from our treatment plant and our source. It could be agricultural drainage, industrial waste, municipal wastewater. For years and years and years in the 19th century, they were going ahead and, basically burying vehicles when they died. And the 20th century, rather. And, so there's been a lot of things buried. If you go around the Central Valley, you have no idea how much farm equipment is buried down there. And again, when you bury farm equipment, over the years, that stuff starts to rot out. And you've got hydraulic tanks in there, you've got gas tanks, oil, all that kind of thing. 1 quart of oil will pollute 1 million gallons of water in an aquifer. So, I see this kind of thing all around. We're in an ag area. And, the more you think about it, the more you're involved with water, the more you're going to think about all those creeks and everything else. And, what are we looking at? Well, we certainly in our surface water, it's soft water, we have a lot of turbidity, we have color, suspended solids, and microbial contamination. Again, this is the stuff that theoretically can make you really sick. So what are some of our other concerns? Minerals from irrigation that damages the fertile soil. Acid rain kills the fish in the mountain lakes. Water shortages influence energy consumption due to the water tables dropping. There's a huge nexus between energy and drought and water consumption. Do you know who the largest user of electricity is in California? It's the water industry. Water recreation must be located away from our intake structures. Obviously, we don't want to be boating right around, where we're going to be using, pulling out of that intake structure. And stratification. What is stratification? Stratification is when the water separates out in zones by temperature. So here we are. This is thermal stratification. And again, this is layers in a reservoir or lake. You have three different specific layers. You need to know these words. The epilinium, the metalinium, and the hypolinium. So you have epi, upper, meta, middle, hypo, below. Now, one of the things that happens in water and reservoirs is these can actually flip. And all of a sudden, all that cold water literally flips over to the top. And again, this is the kind of stuff that can cause havoc when you're a water treatment plant operator, because thermal stratification and flipping of the reservoirs can happen once or twice a year, depending on the climates. So here we go again. The epi is the upper, the warmest layer, which continues to mix. The meta, or the thermocline. That's the one term that is, can be used either way, metalinium or thermocline. It's the metal layer, which is the zone of rapid temperature decrease with depth. And then the hypolinium, which is the coldest layer, which is the denser water. The water gets much denser as it gets colder. And again, the one way to remember that is, what's the densest? Well, when it freezes. So you know it's going that direction as far as, the way it goes. Stratification. The upper layer warms up in the spring, reduces the mixing, and it causes the turnover of a reservoir or lake. And if it's one mixing, it's called monomictic. And if it's two, it's dimictic. So mono 1, di 2. Sanitary surveys, critical. Sanitary surveys should be completed in the beginning to determine capacity in the treatment. Ongoing sanitary surveys ensure water quality, they identify hazards, the treatment requirement, and any potential cross connections. Groundwater, an aquifer. We all should know what an aquifer is at this point. It's an underground layer of porous water-bearing material, which is sand or gravel. We have two types of aquifers. A confined aquifer, which is between two impervious layers of clay or rock, also known as an artesian aquifer, and an unconfined aquifer, which has an impervious layer beneath it, unconfined above. So the water table goes up and goes down with the season of the year. A confined aquifer is buried down between those two layers. It's the really good water that's down below. So let's talk about this a little bit. We have what's called a flowing artesian well. And what an artesian well is it goes down into the confined aquifer, which means it probably has been drilled, and the outlet is lower than what the top of the inlet is in that aquifer. Thus, it naturally pushes the water up. No pumps required. Now, over here, we have it just into a unconfined rather, because the water can come and go in and out of the lake, and it's a well requiring a pump. We obviously have evaporation, transpiration, evaporation, all that kind of good stuff, the precipitation, but that's really how it works. So this is your zone, the confined aquifer of that premium water, much better quality than in an unconfined aquifer. So what is groundwater? Groundwater is basically in the unconfined part of the aquifer that can go up and down with seasonal changes. So in the summer, the groundwater is going to be a lot deeper than it is in the winter, and especially this winter, because we are getting hammered. We have capillary water, which is basically, you can see the air, okay, those little white areas of the air, and then we have saturated, okay, which is, and again, this is all gravel down in the earth. Fractured limestone is by far the most common across the country. Now, we have fractured granite coming out of the Sierras. Very similar, but again, very different. Sources of contamination. Oh, look at that poor little guy down in the well. We have landfills, hazardous waste disposals, improperly abandoned wells, septic systems. Septic systems are one of the biggest causes of nitrates into the earth. Agricultural activities, storm drains, radioactive waste. We have more sources of contamination than we can count or even think about at this point. GWUI, what does that mean? Groundwater under the influence. Or we have GWUDI, which is groundwater under direct influence. So how do you tell the difference? What are we looking at? We're looking at turbidity, temperature, water quality characteristics. Lab testing certainly tells us, and your primacy agency. Now, your primacy agency is your governing agency. So it's that one agency above you that's kind of like, you know, it's that regulatory agency that you have to report to. So, you know, it could be as small as a county environmental health or a city environmental health department. It could go ahead and go up to the state level, or it could go all the way up to the EPA level, your primacy agency. So we have several parts of a groundwater well. We have a sanitary seal. It prevents surface contamination from entry into the well. It's a sanitary seal, you know, and again, think about these words. A well casing, it's the lines the borehole prevents the collapse. The well casing is that steel pipe that goes down inside those wells that, again, keeps all that dirt from going in and collapsing that well. We have a well slab which prevents surface contamination and supports the equipment. It's a slab, it's a concrete piece. We have grout. Grout is used to fill the annular space preventing contamination. And at the bottom, we have a well screen which prevents sand from entering the well. Okay, here we go. Let's take a look at this. We've got our well screen down here. This is actually our pump. Actually, we're on a turbine pump here. Those are the bowls down there. We have a well casing that comes up. The grout is in the annular space, which takes up that void between the pipe and the dirt. We have a poor quality aquifer, and you certainly want to make sure that you deal with that. And the grout prevents the contamination from seeping in. We have the water table down here. Here we have the well slab. You can see the well slab is sloped away from the entrance of the well. The sanitary seal right there, again, that seals the hole. Very important. And again, any abandoned wells, it's really important that they're taken care of correctly, and they need to be capped off completely, and it has to be done by a licensed well driller. So let's talk about a few other things that happen when we're pumping out of a well. Let's start at the bottom. We have our radius of influence. Well, what does that mean? Well, Mrs. Jones is on 1 acre, Mr. Smith is on the next acre. Mr. Smith is pumping water like crazy, and all of a sudden Mrs. Jones doesn't have enough water. Well, she is in the radius of influence of that other well. Our pumping level. What the pumping level is when the pump goes on, it draws down. The water starts up here and it naturally draws down and then equalizes. That's our pumping water level. The drawdown is the difference between the static water level, which means the pump is at rest, not working, and the pumping water level. That's our drawdown. Then we also have a cone of depression. This cone of depression is when you pop a plug on a bathtub, the little like tornado that's going down. That's what that is. It's air. And the same thing happens in the ground as you're pumping. You certainly have your discharge and obviously your ground surface. So well terms. We need to go ahead and know these and understand them. Static water level, normal water level at rest, pumping water level, stabilized water level when pumping over time. The drawdown is the total drop between the static and the pumping water levels. And the cone of depression is in an unconfined aquifer, the cone shape of the pumped water surface. drinking water treatment. The EPA, Environmental Protection Agency, the SDWA. Now this gets together some of the things that we've been talking about, and it really gets into the point of why I had you guys write the letters that you did. The Safe Drinking Water Act was approved in 1974. It gave the EPA the responsibility for developing regulations. The EPA, federal, Environmental Protection Agency, sets the primacy and secondary standards. The EPA requires public water systems to report their sampling results. The EPA sets the guidelines for treatment technologies, and it gave state agencies the choice to assume primacy. In California here, we have the minimum levels from the EPA, but our state levels actually are substantially higher than the national levels. So if you become a certified water operator in California, guess what? You are pre-qualified to basically go work in about half the other states. The EPA set up what's called the multiple barrier approach. So, what are we looking at? Source water protection, sampling, physical treatment, chemical treatment, disinfection, more sampling, and record keeping. You can't keep enough records. And again, we'll get into the historical data side of this at some point, but record keeping is absolutely critical. If you do good record keeping, and a lot of the computers that we're using automatically do data accumulation at this point, and you can look at trending, it allows you to see what happened in similar weather circumstances a year ago or 5 years ago. How was it treated? What did it do? It gives you, actually makes your job a lot easier if you understand how to use the data. Sampling finished water. We do what's called coliform testing. Coliform is a group of bacteria that include both pathogenic and non-pathogenic species. Now that's key. Coliform in itself is actually, it's not pathogenic, it's non-pathogenic, but it's an indicator organism. And if it shows up, that means that there could be pathogenic organisms in there. We use coliform because it's too hard and expensive to test for every pathogen. It is an indicator test. It's an indicator organism. It's more persistent in water than other types of bacteria, and it's always present in fecal contamination. So we got the bullseye. So what is coliform? We have our total coliform out here. Then we go into fecal coliform, and then E. coli. Groundwater treatment. What are some of our considerations? The coliform and E. coli. Influenced by surface water. You know, we talked about those confined and unconfined aquifers. Well, an unconfined aquifer is influenced by surface water. Turbidity. All those floaties. The pH, excessive minerals, and any other SDWA requirements. Again, Safe Drinking Water Act. Groundwater treatment may not be needed for pathogen removal, but it's disinfection only, mineral removal, softening, and corrosion control. Groundwater. Surface water pre-treatment. We're going to have intake screens. You know, we've got, starting in our reservoirs, in our big, huge open reservoirs, we've got these huge screens, and the screens keep going down as it goes through the sections, getting eventually to our water treatment plant. You know, we want to start by getting all those logs out of there and eventually get all the weeds out of there. Aeration adds oxygen and precipitates minerals. Ozone helps disinfect and other treatment processes. Ozone is something that you can use for taste and odor, but you can also use for disinfection. Now, the thing with ozone is it does not last. There is no residual. It is an instantaneous kill, and after that, it can become the water can become contaminated again. Chlorine helps disinfect and other treatment processes, and pre-chlorination can cause THM and increase taste and odor problems. THMs are trihalomethanes. And what they do is basically chlorine reacts with organics. So we want to try to get as much organics out of the water before we treat it with the chlorine. Because the trihalomethanes, basically are a real bad poison that goes out into the atmosphere and the water and all the earth out there. Complete treatment. What are we looking at? Complete treatment is coagulation, which is the addition of chemicals that will clump together with particulates in the water. Flocculation, which is gathering together particulates and coagulant chemicals after coagulation. The sedimentation process then is solid particles settling out of the water and usually in a large basin, and then we do filtration after that, which is the removal of particulate matter by straining, adsorption, absorption, biological action, and sedimentation on the filter media. And obviously then we still have to disinfect. Now, complete treatment is always used for surface water. And the difference is sedimentation. That's the extra step. So here's direct filtration. Our direct filtration is something that we use with our well water, our groundwater. We have our raw water coming in, coagulants and the coagulant aids, rapid mix basin. Again, you add the stuff in, it mixes up real quickly. Then it goes to the flocculation basin where it's got to really slow down because we're trying to get it to clump together, and if we don't slow it down, it'll all start breaking apart. We have our filter aids, which again could be chemicals that we're adding in. We have our filters. Now, on our filters, we have all this crud that we're doing that's going to get stuck in our filters. So we always need to backwash our filters, which means reverse the flow of water and put clean water through, and that's the dirty wash water that we want to dispose of then. But we add disinfection chemicals, and then it goes to our clear well. And again, any water that's being used for filters for backwashing has to be clean water. But after that, it goes out to our distribution system. So treatment plant and the basic objectives is the production of water at a reasonable cost with respect to capital costs, production of water at a reasonable cost with respect to operation and maintenance costs, the production of water that is safe to drink, the production of water that is aesthetically pleasing. Once the water leaves the plant, are you responsible? The distribution operator is. Water can degrade in the distribution system. So we're treating the water in the water treatment plant, and that's the treatment part of it. So that's the operator that's doing that. Then we have the distribution system where it's going out through the lines to the customer's house. Now, in a small water utility, that could be the same group of employees. In a bigger facility, you're going to have specialists. So you're going to have treatment people that work in the treatment plant, and that's all they do is work in a treatment plant. And then you're going to go ahead and also have your distribution people which are out in the field. Water can degrade in the distribution system. Well, if you've ever been in California in summertime and you've taken one of those big 5-gallon white plastic buckets and filled it with water and left it there for a few days in the heat, it starts to grow a scum on the inside of it. That's called a biofilm. We also could need disinfection byproducts that can be created. And again, we got to be careful of that. Corrosion, stupidity or ignorance, well, that's a common thread, unfortunately, for too much of our society these days. And cross connections. What's a cross connection? We've talked about this a little bit, but it's a connection between a drinking water system and an unapproved water supply. So again, what we're looking at, we've got a wellhead, we've got a drinking water hose that's feeding into the cattle trough. Now, if all of a sudden we get some back siphonage, what's going to happen? It's going to come right down this hose and go right down into our well and taint that aquifer below the ground. Now, that's when we get into polluting our aquifers